daha fazla pardon. Böyle internete girdiğim zaman onu bakıyoruz. Hatta böyle 3-5 lira falan. Ben de bir kartında bundan 3-5 lira geçirmiyorum. 1 lira falan. Daha bir gün saçmaz böyle.
Okay, let's start. Good morning. So this is the final lectures of the quantum field theory. Yes, my goodness second. So since it's the last day of my lectures, for the general audience, let me remind you about the parallel sessions for next week. Some of you have already come and talked to me about their interest to participate in the parallel theory sessions. So it will be good that you told me or sent me. My email address is my first name dot last name at CERN. So if you are interested in these parallel sessions, please send me an email. So I established the list, and we also made more or less schedules which I'm going to post or distribute like at the beginning of the next week or tomorrow. And please, somebody remind me about the list which needs to be shown again. Okay, so yesterday I tried to introduce Feynman path integrals, and I did it more carefully for the quantum mechanics, and then took our map from quantum mechanics to field theory, where we were replacing the coordinates with the fields and the conjugate momenta with the conjugate momenta of the fields. And we arrived, we were able to, after hand waving, integrate out the momenta integral, and we got the path integral for the scalar field. And some of you asked me, obviously, what the advantage of the path integral is. One of the advantages of the path integral is it's made the symmetries of the theory manifest. And also, if you start with classical mechanics, you just write down the Lagrangian density, and you write down the measure, and then you have the quantum theory. As Metin pointed out yesterday, one of the differences is in Hamiltonian picture you are dealing with operators, whereas in the path integral you are just dealing with the functions. But the functional integral is usually very hard to do, especially when you have interactions. You can perform the functional integrals when you have free theory, but if you have interactions, you cannot do the path integral. So then, for that you have the perturbation theory, and Altu has already introduced the Feynman diagram to compute in the perturbative series, how to get contributions. But he didn't derive the Feynman rules. He just explicitly stated them, and I wish I could go in detail on how to drag them and talk about weak contraction, but I don't have time because I want to move on with the gauge theories today. But before that, I just want to give you very sketchy, in a very sketchy way, one of the advantages, how to get this contributions from the path integrals. And this is actually one of the advantages, because if you are doing this kind of computation, perturbative computations, or this weak contraction in this Heisenberg picture, in the Hamiltonian picture with this interaction Hamiltonian, then it's very messy. But it becomes really smooth and nice and clean when you do the path integral formulation. And I will try to distribute some notes and some copies from Peskin and Schroeder by Monday, so where you can see how this computation is done in the Hamiltonian formalism, and how this computation is becomes easy on the pattern table. So, okay, so if you have to do like, this perturbative computation, for example, you have like, scalar field, so we have this scalar field Lagrangian, let's say. Okay, so this is, let's say, we have this free part of Lagrangian, which we have been writing down. And imagine you also add like, 5 to the 4th term. Okay? So if you add this 5 to the 4th term, the theory becomes non-interactive. And here you will treat the lambda as a small parameter and make an expansion in lambda. So if you do that, you will eventually you will need to compute things like, let's say, I'm just giving it as an example, and I'm going to be very, very hand-wavy. So then let's make this the integral, and then you need to be careful about time ordering and how to contract them, how to order your coordinates, and it becomes a mess. Okay. So the clean way, and you can get something. Okay? You can get the result in the homotonic picture. The clean way to do this is, once you have your pattern integral, you can create a generating function, or generating functional. Okay. So in the generating functional, so this is your pattern integral, let's say free plus interaction. So you have the action for that. Plus, you introduce terms like this. So in addition to the action, which includes interaction in the free part, you add a source term. That's why when one of your friends asked about the source, I was kind of confused because this is also used as a source. So then, what you can do is, to compute the time-ordered correlation functions, you will, it turns out you need to insert, okay, maybe I should say this, so this is what you get in the Hamiltonian formalism, but in the pattern integral, if you are looking the time-ordered correlation function of some fields, let's say 1 n, roughly, it's just inserting these operators in the pattern table.
Sorry.
Yes.
The meaning of the additional term is
which ones?
In Lagrangian. We can say that field interacts with itself.
Yeah, more or less.
And in the last line, what is the additional term J?
This.
You say so.
Yeah, this is a new field we are adding, okay? And it will become clear its meaning.
Why comes from the expansion of the Lagrangian?
No. I'm just introducing by hand. This is I'm introduced by hand. This one. Okay, what I'm going to do is, let me just finish here. So if you, in the pattern integral formulation, you can show the time order correlation functions are related to can be calculated in the pattern integral by inserting these operators in the integrand pattern integral. So you have to do this. So since this is my recipe, the good thing about this J, I can functionally differentiate J. It is the generating function with respect to J. And every time I differentiate this Z of J with respect to J, then I will bring down one term, one field. Right? If I differentiate with respect to this, I will bring it down a 5. If I do it for the second time, I will bring another one. And if I do it carefully, then actually like you can see, you can compute the correlation functions as like a functional derivative of this like generating function. And in this formalism, like you will see if you just do like if you have like multiple, let's say I'm going to just J1, and then you do it again. You can do it like multiple times. For example, just be a little bit more careful. So let's say you do x1, you can also do x2. Because I mean, this okay. This, when I said like phi1, this is the phi operating instead of x1. This is instead of xn. So if I just like careful like differentiate with respect to this x1, x2, and that, so I can actually eventually bring all these factors down. If I can compute this, then I can just take the functional derivatives and compute this like multiple point functions which are in the perturbation theory, which are very hard to compute in the Hamiltonian formulation. But as I said, I mean, this is supposed to be very hand-wavy, and I don't want to go into details because I don't want to gauge theories. And I think it will be good. Like, this is, you will find this in any like generic quantum theory book. So how to get this like Feynman rules and reconstruction from path integral. So since you know the path integrals and you kind of have a rough idea how this procedure like goes, I think you can work out the details yourself. But I mean, we will be here together for another week, so I mean, feel free to come and talk to me about this. Okay. So let me start with the gauge theories. Okay. So one of the simplest gauge theories is the QED. And Altuve has already written down Lagrangian for QED. Let me repeat. So it has a Dirac part, okay, which governs the dynamics of the fermions, which we didn't have time, I guess, to go into full detail. So then you have the Maxwell part, which controls like electromagnetic interaction, and then the interaction part, which includes the interactions between the fermionic fields and the Maxwell field. And explicitly, and this term you know from your homework. And you also have this actually where you see the interaction of two fermions with the gauge field. And later people like realize, I mean, or like they immediately realize when they wrote down this interaction. This can be written in a more compact way if we replace this like usual partial derivative. It was called like the covariant derivative. So then QED Lagrangian takes the simple form. And here, what I did, I haven't done anything but I defined as my capital letter, capital E, mu, covariant derivative, I combine partial derivative with the gauge field. So once you have the Lagrangian, and remember we were talking about like symmetry, and it turns out the QED Lagrangian is symmetric under this transformation. if you take the fermionic Dirac field and rotate its phase, this Lagrangian stays invariant. But here, you are not only allowed to do global changes, global rotations, where alpha is independent of your position. You can also do local transformations. So meaning at every different space-time point, you can give your fermionic fields another phase. And still, like, the Lagrangian, the QED Lagrangian will be invariant if you also shift your, vector potential like this. Okay. Here, these are local phase rotations. And as I said, the point is, the crucial point is, the rotations are the base rotations are arbitrary from point to point. Actually, you have seen the symmetry before in when you were studying Maxwell's equations, because when you look at the study solutions, curl of B is 0, and one of the solutions for curl of B is 0 is when B is written, you know that you don't have any magnetic monopoles. That's why the divergence of B vanishes. And one of the ways to write this as a solution is if you write the magnetic field as the curl of an A, and there you're allowed to do gauge transformations without changing the magnetic field. Once you have the A, you can always shift that by derivative of a function. Okay. So the Lagrangian, so if you want this to be the symmetry, is that arbitrary rotations. For example, one of the allowed terms you can put in the Lagrangian is the mass term. Okay, so then n, what is allowed? But you will see that these gauge transformations are going to put some restrictions on which fields we are allowed to put into the Lagrangian. Eventually you will see, that you may not get a potential or a mass term for the gauge bosons, which is a squared. Okay, so here, if the field, if the field is not doesn't include any derivatives in it, or if the terms have only fields without their derivatives, that's fine. They will come with complex conjugate and they will cancel each other. But if the term in Lagrangian has a derivative, you need to be more careful, because once you make your gauge transformation, your phase rotations, the derivative is now acting also on the space because it's local, but it depends on x. Excuse me. But when you're taking the derivative, it's not it's local, but it's also an operation where you are comparing the fields at two different points. And then you just take the difference and take the distance to 0. But as I said, the Lagrangian is invariant under this local phase rotations, and I'm allowed to rotate the phase arbitrarily at different points. As I said, so I can rotate the field at one way, and I can rotate it in the other way. So then when I'm comparing them, I need to find a procedure to make it to make the comparison nicely. So if you write it more carefully, so the derivative is defined as, if I'm looking at derivative in a particular direction, and the fields are rotated differently at two different points. So people, I mean, among you, like, who have seen GR, actually knows this, like, phenomenon very well. I mean, if you have a curved space-time, when you're taking derivative, you need to be careful. Right? You need to, like, first, like, translate your vector from one space point to the other, and then carefully, like, rotate it along the path you're taking your, like, your vectors. And that's why you introduce what's called connection. Because when you're taking the derivatives at two different points, again, like, those vectors live on different spaces. Because at each point on your space-time or on your manifold, you have a tangent space, and the vectors live there. And at another point, you have another space, and you're actually comparing vectors from two different vector spaces. So you need to make first the translation going from one vector space to the other, and you need to be careful how the vector is rotated around the path you're taking from one vector space to the other, and then compare them at one of these, like, vector spaces. And there, this transformation, this rotation of the vector is described by the connection. And let me tell you the answer first. I will try to convince you that here our vector potential is actually the connection, similar to the connection you see in GR. So yes.
Okay, this is connection.
This one will turn out the connections.
Okay. What corresponds to curvature factor?
F mu. And I will try to convince you that F mu as well.
And second question, what is N mu?
This is like the function, I mean, the directional derivative. So you are taking the derivative along the direction n. So I mean, you start with x and n plus f. This n is like a 4 vector pointing like in one direction along which you want to take the derivative. Okay? So because of the reasons I said, like this derivative has no geometric meaning by itself. So for this, I mean, we need to introduce some sort of a function or some sort of procedure where we are taking, like, let's say, the spinors from one place to the other. And one possibility is this: if you have, let's say, consider functions like 2 points. It's obvious it has to be like a function of 2 points because we want to transit from one point to the other. And let's impose transformation properties on the equation like this. Imagine I just like introduce compensator, and you will see like why it's called compensator in a second. And I want the compensator to be transformed in this non-trivial way under my gauge transformations. And of course, it has to be 1 if x and y are the same points. If I'm at the same point, I don't need to compensate for anything. They're at the same point, so it has to be equal to 1. So the point is, if you look at the transformation properties of this stuff, rather than such alone, but with this compensator, you see that this is going to, amplification transformation is going to be and this is how U transforms, and I also know how psi transforms, so this is like what it's sort of base. They cancel, and this object actually looks like it transforms like psi at y, because if I transform the gauge, it's going to be so this object, the field, the compensator field, transforms the same way as the field at a different point. So now it makes sense to take their difference, because now I know that both fields are transforming the same way. So this is going to be our definition for the covariant derivative. So I started with x, kind of translated to a point which is in the neighborhood of x, in the epsilon neighborhood of x in the n direction. It will have the same transformation properties as like the field, like at that point. Now I can take the difference and like divide by epsilon and take epsilon go to 0. Okay, so here, okay, we are going to assume something. We are going to assume it's an assumption. We are going to base our calculations based on this. This is a pure phrase. And here is so just by this definition, we should first understand the behavior of U under if the 2 points of its arguments are infinitesimally close to each other. So since it's a pure phase, one of the conclusions as we can say, it is a continuous function of positions. So then I can Taylor series expand this. Okay, so here I introduce this E, I just factor this out for later convenience. And I'm free to do this. I could have also absorbed this E into A, but I rather factor the electric charge out of A. So now, if in this Fourier expansion, okay, this appears as a new field. Okay, in the infinitesimal limit. Of the compensator. Right? I mean, for the moment, you can forget about this part, this discussion, where A had the meaning of local gauge, the gauge field. Just start with the fact, okay, we want to have this symmetry of our theory. So let me tell you what I'm trying to do right now. I'm trying to actually construct this Lagrangian. So this Lagrangian was given, we knew this Lagrangian, Alto told you already. But now I want to try to derive this Lagrangian from the local symmetry. Meaning, I want to construct a Lagrangian such that it's invariant under local phase rotations. And I'm going to construct it.
So I have a question. When I look at the right hand side of the U side at the top, yeah, this equation is like U is the operator there. It seems like U is an operator, but you assume it's a pure phase. So
why is it operator?
I mean, because the psi is like the eigenvalue of the eigenvector of the operator.
No. No.
But
No, this is not equality, by the way. This is like, okay, you start with this field and apply the gauge rotations.
So you just take the field from point X and carries it to point Y.
More or less.
One more question.
Let's make it clear. This is not like an equality sign. I'm not saying this is equal to that. What I'm saying is, I said, okay, since like, I failed here. These are free, right? I cannot do this like in a meaningful way. So that's why I said, okay, let me introduce this field, or an object which transforms, I'm demanding by hand, which transforms like this under the gauge transformation. And if I look at this object, like the product of these two, this has the same gauge transformation properties, like the field and other points.
So if we know the value of the field at one point and if we know u, can we calculate the field at another point?
Yes.
Do we
No.
need to know the derivative of the field or something like that?
I think you should be able to. You should be able to do like infinitesimally. Because this is like, like in the jealousy equations, right? You can integrate them. So you start with that point, you give the initial conditions. If you know the connection, then you can actually consider the integral of the whole jealousy. And you can go from one point. Or if you know like the connection explicitly, then if you start with a vector and see like along a given path how this vector rotates, you can compute this.
If you know at mu, we can calculate u by x.
Yes.
No,
But I mean, this is like, here I'm just assuming this, like assuming, basically here I'm assuming more or less like, u is well behaved. It's a continuous, I can like make a Taylor series expansion, and I'm looking like, when like, it's so I imagine that if you're looking at epsilon, you can always like exponentiate it. Like this is like in Legos. Exponential and get like an arbitrary. For example,
it's like a flow.
yeah, or like in rotations. Right? To get the commutators, you look like infinitesimal to get them. Once you get them from that algebra, you can actually exponentiate that and like recover the full rotation field. So here you should be able to do that as well. Yeah. So, and as I said, I didn't do anything but like a Taylor series expansion, where I'm just like I will have like derivatives. I mean, some directional terms denoted by n, and I introduce vector field as the first in the linear order in this expansion corresponding to u. And but this part is important. So here, I mean, this is more or less like you know the Dirac field. Like a variable in this actually introduces the magnetic field, and you just guess an interaction term which is consistent in symmetries and like dimensionally. And you can construct UED. And then you can look at this and say, oh, this is like invariant under this phase rotations. But here what I'm trying to do is going the other way around. I said, let me start with like the symmetries of like local phase rotations and see whether I can construct this Lagrangian. Because when I do this, then this is going to be a natural realization of this like Lagrangian, which is going to be useful for standard model, meaning that you will end up with non-abelian theories. So once I have the expansion, infinitesimal expansion, it's good enough for me to plug this in here and try to like guess what the mu is. At this level, I don't know what the mu is. Once again, here I said, okay, I cannot do this answer with the simple partial differentiation, I need to introduce this, and then I define here a new derivative, and then I seriously expand it because I need to know the behavior of u, and I'm like infinitesimally separate points, and I'm going to find out what d is, and of course d is going to turn out to be what we had d already on this when I erased. Okay, so n mu is going to be right, so I'm also I expanded u in epsilon and kept the first linear term and ignored all the remaining ones. So I'm also expanding the direction of the first order in epsilon. So there are some simplifications. So first of all, this one. Then everything is linear in epsilon. I cancel this epsilon. And I can factor out and mu, so this is plus I and if I compare the left and right hand side, this is the mu, and this is actually what we have written down before. So one thing you can show is, so you know the expansion of u and its relationship to a mu, and you also know how to transform u under the gauge rotation. So you can combine these two, right? I mean, you can start with this and plug this in, and this is going to dictate you how a is transformed. So if you proceed like that, you will realize A will rotate like this. This is the gauge transformation you knew for A, and we kind of drive it here, starting with these definitions and imposing like invariance on the transformation, which brings us to the point that I want you to show this as a homework. Start with this. Use the expansion and show how the gauge field is transforming. So then check something, okay? Check. And this I'm going to check myself. So okay, if I have derivative with respect to me, the current derivative of the field. So how does it transform under the gauge transformation? So let's try it. Okay, so here I know how A transforms. So I will just plug it in. I know how my field psi is transforming. Okay, so now I need to be careful because when I'm acting with mu on this, I think I need to use the product rule. So let's do this. It's going to give me an I out of x plus leaving the phase and I'm going to differentiate this one plus I A B minus I, so E cancels E I. And I immediately say cancellation of these two terms. And I can factor out this, like, the phase, so I will just end up with I x. Which is nothing but so we realized here that covariant derivative of psi is transforming the same way as psi itself under the gauge transformations. It just takes up a phase, unlike the partial derivative. So now we found a way to construct, like, Lagrangians. Once we found out this covariant derivative, which transforms as fields. So one thing we can do is we can replace, because this kind of means actually like d mu is kind of invariant under the gauge transformations, right? Because this was already like the phase transformation of the field, and that's the same phase transformation even if you acted on it with the field, with the covariant derivative. So in the way we remember that you were saying, like we could introduce the mass term, right? And this was invariant under gauge transformation. So we also know like we have this property, and whenever we see like a derivative, partial derivative, we can replace it with d mu. And we need to be, of course, careful, because when we are doing this, you need to be, there's a guiding principle, which is any combination of d mu phi and phi, which is globally invariant under phase rotations, under local phase rotations, is also invariant. Sorry, which globally invariant under phase rotations. Globally invariant under phase rotations is also invariant under local phase rotations.
Do we
say after we replace the derivative with covariant derivative?
Yes.
How can you say this directly?
Because the idea is like, so if, the key point is like, that this is invariant under the space relations. So this transform is the same as the field itself. For example, how should I say this? For example, here in this one. Okay. If you look at the global ones, this is invariant. Okay. So the statement is, take this one, replace the partial with the covariant, and make it like, this, local. This will be invariant because, this field is transformed like, is unaffected by that, and the rest is taken care of by those, phases, local fields.
But the Lagrangian doesn't change at all when you make this change?
No. And the way we construct it doesn't, it's not changing. This is clear? So if it's like invariant under this, under the global, because the thing is, for the global, then the derivative is is invariant, doesn't care. If that's true, then we show for the gauge transformation, the covariant derivative is acting the same way. So whatever is true for global transformations has to be true for local if you do the proper regression.
And also, can we represent local transformation differently from this form, e to the I false?
This?
Yes.
Why?
Can we represent it differently? What I mean, instead of exponential function.
No, but this is this kind of comes from the league theory, right? Because you get the group action. Because so here,
But I mean, does exist other kind of transformations which we can call local? Because covariant derivative depends on it, and it's also.
Let me put it this way. As far as I know, you can always exponentiate. It's always an exponential. And this goes back to the least theory. That you start least theory D. There you start with you look at the algebra around to infinity, around to unity, and then you can exponentiate to get any arbitrary. As long as you are dealing with the legal, I think that's the case.
We are only interested in the
That's why everything's going to be exponentiate. Start with the algebra, and then any arbitrary element of the group can be obtained by exponentiating some element in the algebra, some unique combination of groups. But you need to be careful too, because for exceptional groups, you have gauge theories which don't have a Lagrangian description. So that weird case is also possible.
So it can be
Well, you can have other constructions. There are other, you don't, to define a gauge theory, that's not the unique way to define them. To write on a Lagrangian, and that's one way. But there are also cases where maybe it's just our lack of understanding that we cannot construct a Lagrangian description for the gauge theory, but by other means we know that gauge theory exists and has an exceptional group as it's legal or symmetrical. That exists.
what we demand for say that this is gauge theory.
When there's a gauge transformation. But okay, we are just going to a different path. But there are cases even you start with an SUN theory, and you do the flow, and you just end up with an exceptional group, just go to a patch of the modular space where you don't have a Lagrangian description. That's possible too. But that's completely like, we should not discuss this here right now.
So this alpha is just some kind of parameter, right?
Alpha is an element in the actually the algebra.
Yeah. So is that something? Does it have something to do with the electric charge? I mean, you don't
Yes.
Yeah. So if we have more charge, we have more parameters.
Yes. I mean, actually, when you have like the more complicated Lie groups, then you have lattices where you are representing like the roots, and then you also have like co-lattices. Complementary, like where you can define this inner product like between them, and then you can actually show that electric charges corresponds to vectors in one lattice, and magnetic charges corresponds to in the other lattice. And in gauge theory, there what's called like the duality, which is like exchanging the decoupling regime with the strong decoupling regime. In that case, you, for example, exchange the lattices. So there is a very like intimate connection to Lie group theory. Lie groups, and those lattices, those start making sense like as charges, electric charges. But it's again like not like immediate approximity for us right now. Okay, so now, since as I said, our aim is to construct the Lagrangian, then you may say, this looks like, with this time with this covariant derivative, this looks like only the kinetic term of the fermions coupled to the electric gauge field. Right? Remember our gauge field has something like this. With an aspect. So we constructed that part of the Lagrangian where we have this like fermions coupled to the electric field. But we also have this kinetic term for the gauge field. So how do we construct this? Okay. So since I know the answer, let me start computing something and then show you that we are getting F medium, what we know as F medium. And for that, it turns out we need a little bit more than the linear term in X of U. Remember, like I erased the expression where I expanded this U up to the linear term. But if you do this and perform the computation, what I'm about to perform, then you realize you'll get 0. To get something non-vanishing, you have to go to the second order. And in the second order, it will have this form. I'm just now pushing I'm looking at it like a mu, not at x, but like shifting that. So this is going to be my second order. And we want to check what's called the connection. So one of your friends asked me what F mu will be, and F mu will be the connection, no, not the connection, so the curvature. We have the connection, and let's compute the curvature. How do we compute the curvature? One way, the geometric way, is to take a vector and rotate it around the loop. Okay. So that's what I'm going to do. So I'm going to start at a point x, then move to x plus epsilon, and we'll denote it like as a vector 1, go up, go left. This is my point 2, and go back. So I will close the loop around the point x. This is the standard way you compute the curvature in Riemann geometry. So then I will define an object that I'm going to call u bar, and that's only going to be a function of u, of x. because coming back to x. So let's do this. So then let me start from here. First, I will go from x to x plus epsilon 1. Then I will go from that point epsilon 1, epsilon 2. So I will start here. I hope it's visible. And so I was, okay, so I start here, then move to this point, and I was here, move to this point. So now I'm going to move from here to here. So this is going to be here. U. This is U, this is N. So I close my loop. Yes?
I don't understand which vector is which. What's epsilon 2?
Okay, this is one vector, one direction. Two.
All the way around.
No, okay, so the definition of you go from x to y. Okay, so I start with x, go to x plus, so that I go from that point, I go here. From that point, I go to here. From here, I go to here. I mean, okay, you may be confused about this minus plus signs, but they don't denote the direction of the arrow. The direction of the arrow pointing the direction of the line is actually encoded of the order of arguments. From where I go. I mean, these are just the locations of those points. But the arrow, like the way I go around the loop, are denoted by my initial and final points, or like the order of arguments in it. U, x, y, or y, x. I start with x, go to u, I go to y. Then u, I mean, what I told you x is embedded. Under phase rotations. Right? Because y is invariant. I know the transformation, remember the transformation properties of u. So you will have, if you just look at the first one, you will have I minus I epsilon x. You have here I epsilon, sorry, I alpha x plus epsilon 1. But here you will have the minus 1. Yes. Right, so this like in the intermediate like between u's, they will cancel each other. Cancel, 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 and here I will have x. This will cancel this. So the object I constructed by going around the loop is gauge invariant. It's not picking up in your face. And this could be your second homework. To show or you can check it yourself. I should probably not use this as a homework. So what you need to show is, or what you can show is, start with these expressions, okay, with this expansion. Plug this in here. Do a bunch of manipulation, and then you will end up with this expression. 1 minus E. So now I hope it's clear why I said like we need to go to epsilon squared, because if we have done this computation by the order of epsilon, you wouldn't catch this one. So to catch something non-trivial, you need to go to the higher order. And it should be already clear, because up here we pick like particular direction, like the first and second directions, x1 and x2. But if you do it arbitrarily, then you get it. Which is locally invariant. So you see, I just demand like local phase transformation or invariance on the local phase transformation. So I define my connection or the compensator. I look at the curvature of that connection, and I eventually end up with F mu. And this description is going to be, this here we are in U1 theory, enabling theory, QED. But if you just, as I say, like you go to higher, gauge groups, like higher rank gauge groups, the interpretation, of A as a connection and F as a curvature, still correct. And as I said before, okay, this is a point. So I mean, since this F mu is a gauge invariant object, so you can actually start constructing kinetic term or other gauge theory terms using F mu. And you may wonder, I told you, but let me just also write explicitly about something like this. Possible mass term for the gauge field. It should be clear by now this is not gauge invariant, so you are not allowed to insert this in the Lagrangian. But let's say F mu is gauge invariant, and it's allowed. And actually that's your kinetic term. So basically we constructed QED. We started with local invariance and did a little bit of math and eventually got all the objects we need to construct QED. So another thing you can check is the commutator of d mu. If you look how it's transformed under the gauge transformation, you see it's also invariant. Because we have this factor, phase factor, coming from field. And more importantly, what we can check is mu. And this is your homework.
Do we need the direct equation to do this? Then there's one side here at the left, right?
You mean here?
Yeah.
Okay, this is the pure gauge part. And of course, using these, you can introduce other interactions. And that's, I'm about to show you some renormalizable and non-renormalizable interactions, which respect Lorentz invariance, respect the gauge invariance. And first, I'm going to try to build dimension 4 operators, Lagrangian, which are going to be normalizable, and then higher dimensional operators, or higher dimensional terms, not operators. So okay, this is clear, right? This is the homework.
gives something like BF.
Yeah, I mean, yes. I mean, this can, you can also show like, you know, I mean, this is going to be anti-symmetric. And it's coordinates, and then you can actually then, for example, then you can show that they satisfy the Jacobi identity. If you also introduce like, you know, a derivative. You can also, you know, relate them to the actual identity. Okay, the four one, the dimension 4 operators are so this is an allowed operator, or an allowed operator, allowed term. You know this one. This is allowed too. But you have something more interesting. What is this one? So here you have these two different, like two Gaussian fields. You can contract them with this Lorentz invariant tensor. That's an interesting Q term in the dimension. Minus the mass term for the fermions. So if you require Gaussian invariance, Lorentz invariance, dimensional normalizability, you eventually end up with the Lagrangian plus some additional term you haven't seen before.
What's the meaning of 4? What's the meaning of 4? Why you put L?
4? Okay, so right, so this is like, you know, inverse dimension 4. So make it like, you know, dimensionless. This is a requirement for like normalizability. I mean, the coupling constant, like, you know, behave nicely, like, you know, behave nicely. But you can also like introduce like higher, because I mean, if you have the coupling constancy, for example, if you go up to 6th order, then the coupling constant starts having like, you know, dimensions of mass. And the way they have like the dimensions of mass, like inverse or like a proportional to the mass, is going to tell you like, you know, whether those terms are going to be renormalizable or non-renormalizable.
What is the tensor epsilon?
Okay, so epsilon is like, you know, this totally antisymmetric tensor with probably convention like 1, 2, 3, 4 is equal to plus 1 or minus, I don't know. No, that's not, it's just like, yeah. This is like for higher indices.
Could you repeat the discussion that the reason for
Four? Okay, so let's start. Okay, so one thing you can look at is like the kinetic terms. Okay? So here, so this is like a partial derivative. So this is like, you know, dimensional inverse. Dimension of mass. And if it has to be 4, because I mean, this is like, this appears in this Lagrangian, to make it like, you know, have dimension of 0 mass, this has to be met with 3 half. Okay? So then this is like 3 half, 1, so it's also dimension 4. So for the gauge field, so this term has dimension 2. So you have the derivative at mu, 1. This is dimension 2. So also this is dimension 2.
We are trying to determine the dimensions of cages.
Sorry?
We are trying to determine the dimension of cages.
Yeah, and by looking at the kinetic term, like, you know, by looking at the terms, I mean, we can determine the dimension, and then you can actually construct. You look at all possible, like, you know, combinations, which are gauge invariant, Lorentz invariant, and let's go together.
Ben bir consideration bir on consumer.
Why?
Sorry. When we try to construct
Okay. You have interaction here.
Okay.
Right, and here it's in the covalent derivative, you have the A mu that couples to the term fermions. You have interaction here. And once we have like the non-abelian theories, this will also have interaction of radiation, a non-trivial interaction with itself.
Can I ask one more?
Sure.
We showed that these terms are getting varied, but what made us put them into Lagrange? Like, why did we add them on the Lagrange? Why do we have a curvature term in Lagrange? I mean, is it supposed to be like that?
I mean, you want to get the kinetic term for the gauge field. And one thing you can look at is the curvature. Since it's a connection, you can look at the curvature, and that acts like, the kinetic term.
So we knew that we should put a curvature term in the Lagrange.
No, we didn't. We just. No, here we have all possible terms with this property, satisfying the symmetries. And that happened to be also like, the Lagrange opportunity.
May there be any other term that's going to vary that has something to do with Lagrange?
Sure, I mean, those are the terms I'm going to. So this is like, if you demand, this is like up to 4 order. I mean, 4th dimension 4. This is all what you have. I mean, sure, you can have other charged particles. If you have other fermions, you can have make them like other. But you can introduce a number of fermions, but then this is generic form. If you have 6, I mean, you can have things like this is like 3 3, and then this is 2, this is 5, this is actually 5, 6. It has also an operator as dimension 5. And this is 3 squared 6. So you can probably add more terms, but they're all going to be Lagrange.
Is it C mu? What's that? Sigma mu?
C no C3.
No, in the first term.
Sigma medium.
Which is
Sounds like, combination of the power matrices. Okay, and here we demanded U1 theory. This is Maxwell. Because we allow only local gauge transformations. Only phase which is like kind of either.
I can respond. Why do you consider dimension 6 and dimension 5?
Oh, okay.
Before in mass dimension.
Yes. But then, then the sculpting cluster will also have mass. They're going to be massive. I mean, they will also have, they will also carry some mass. So
Something like -1 to
yeah, that's possible. But the thing is, okay, so usually what you get, you get these non-normalizable terms if you integrate out the heavy fields. For example, you have a theory with many fields, okay? And then some of them are very heavy, and you are not interested in the dynamics of that, you are just interested in low-energy dynamics. So you can actually integrate those interactions out. So once you integrate those interactions out, you will get new terms in your Lagrangian whose coefficients are related to 1 over mass square. So those interactions, those terms are going to be less significant, more massive the particles you are integrated out. They are really, really heavy, just decouple them. So it's called they decouple from the theory. So there are many theories, for example, although you have many heavy particles, you don't need to really worry about them because their interaction, they are effect. It's really negligible for the low energy dynamics. And then you get if you want to include them, then you can actually. But these theories are kind of sick because they are valid only up to the up to the energy of the particle which you have integrated out. Because this is kind of like an artifact, or this is like a term which is like, which is there after integrating some particle out and getting rid of that particle in your Lagrangian, making your path integral simpler. Because then you have like, integral with respect to all fields, and this terms will appear if you do the part of the path integral. If you perform the part of the path integral corresponds to the static fields, then that path integral is dangerous. But the prizes, and you get like these terms in your Lagrangian. Okay, and then the description is only valid until the until the energies when you have the mass of the particle you integrate it out. If you want to go above this, then you need to be careful. You need to go through UV description. But there are also more pathological cases when the particles are becoming massless. Then your description breaks down because you have energies. You think you integrated them out, but they can be massless and go below the energy scale you're integrating. Then you have problems. You need to be very careful then. So when you are dealing with effective theories, you really need to be very careful what it means, what you're doing, or what the terms are included in what regime you're looking into your theory.
For instance, in gravitational theories, the coupling constant includes less
Yes.
to the squared terms. So, is this gravitational theories
Non-invariant.
non-invariant?
Non-normalizable.
Is this invariant under Gauge transformers?
You can introduce, as far as I'm not an expert on this, I think you can introduce gauge fields in the gravitational fields. But the gravitational field, it's a gauge theory, but it's not, if you want to talk about a gauge theory like QED, you need to introduce it by hand.
But the coupling constant includes mass work, we cannot be normalized.
Okay, that means, it's more careful. It depends how it mass. Because, you can actually have also it depends. Whether it's proportional or inverse proportional. So how much time do I have left? So I have 10 minutes, so let me continue. Okay, so here, so far, so let me just say a couple words about Young Mills. So we consider local based transformations, but now, the expertise we have, we may do something fancier and go, you can demand invariance under continuous symmetry groups, such as SU2. Okay? So that the field, let's say, becomes, you can look at the dot of SU2. Then, gauge transformation will take the form of, instead of remember, we were only multiplying with the phase, but they're going to be a little bit less trivial. Instead of, okay, now since I'm talking about theories symmetry groups like SU2, now I have matrices rather than numbers in the exponential, in the exponent. Now I'm just looking at gauge transformation of this form. And so here, if I don't let my alpha be a function of x, this is still a global transformation. Right? This, if I just act the derivative will pass through this exponential unless alpha is dependent on x. Like in the previous case, remember in the complex Klein-Gordon, in your first one, in the complex Klein-Gordon, you had e to the I alpha. And alpha wasn't a function of x that was global. So now, today, we said, okay, let's make that alpha, that phase rotation local, and we have to introduce this connection. And here, in this format, this is going to be a global, but higher rank symmetry. Okay, and they are usually called like R symmetries. But we can gauge this. By gauging, I can make it position dependent. All this and E, B, S. Yes. Exponential. Okay. But now, there is a problem because in the previous case, we only had alpha and we didn't have to worry about about whether things were commuting or not. Here we need to worry about it because now we are exponentiating Pauli matrices for SU2 case specifically. And rotations only commute when they're infinitesimal. They're not infinitesimal rotations if they're rotations with an arbitrary angle, then they don't commute. So that's why we now talk about non-abelian gauge theories. So this introduced a non-abelian structure of the gauge group. And we are doing this more or less the same thing. We again define the compensator. So everything now is going to be the same, but we need to be more careful about generators of Lie groups and whether they commute or not. So now I'm replacing this, with this e to the I alpha y. I'm replacing with this non-trivial matrix phase rotation because it's this is a matrix acting on this outlet. And you realize actually if you go back to the definitions and get rid of this Pauli matrices, you will go back to the abelian case. If I again look at this infinitesimal U, infinitesimal distance between the arguments of U, I will get 1 plus G. Now this is going to replace the electric charge E. I'm just also factoring this out. Mu. This was more or less what I had before, right? The previous one. But now I also have a sum over the different directions of rotation. Okay, if we repeat what we have done before, we go from U to D by really, taking this infinitesimal or this linear approximation to U and putting it into the definition of covariant derivative. If we do the same thing, then we end up with this expression. Again, the only difference is now we have this explicit sum over the algebra. And okay, let me again remind you. So the next thing we did was we knew how U was transforming under. So we knew in the abelian case how U was transforming. We knew its infinitesimal form, and then we plugged this into this expression and said and find out how the gauge field was transforming under this rotation. So we can do the same thing, and we will get this. So far so good. So it's just if you ignore the sigmas, Okay, this is what we have already. So this is the form that 1 over E is replaced now with 1 over G. Derivative. Now, because of this non-commutative behavior of the algebra, we get this additional terms, or additional terms. So this is new. This is reflecting like the non-commutative behavior of the H field. Or it's the reflection of the fact that, because again, in the U1 case, in the phase rotations, right? So if you rotate like first with alpha 1 here, and then rotate with alpha 2 here, it's the same as rotating like with alpha 2 first, and alpha 3 with alpha 1 later. So they commute. But that's not true for like, SU2. If you rotate, let's say, along the y-axis first and then the x-axis, and then do this rotations in the opposite order, then they're not going to be the same, the end result. But here for the U1 value, only have like phase rotations. They commute. Right? So that's why it was a U1 theory. But here, they don't commute. And that's why the non-commutative behavior of the symmetry group is reflected by this. The appearance of this commutator. If you say like the generators of U1 theory commutate because there's only one, so then actually you wouldn't have this one because it's commuting, like you only have also one generator. So we also know, argue that like in the fermions are inverted, transforming like this. And this follows right here. You just Taylor expand the exponential and look at the leading order. Take this and look at this again. So you will do the same thing again. You just like, plug this expression, like, take this here, manipulate, okay? Then you will see and this should be familiar from our previous expression. Remember, for the abelian case, we discovered this. So this is non-abelian. For the abelian case, we had so this is the same, right? Because this is the linear approximation to the exponential.
Why do we have to do the linear?
Make it simpler.
Yeah, so it doesn't show up like the one. So it doesn't show up like the abelian one if you don't do the approximation.
Yes, but if you don't, okay, so then the question is that what do you mean the exponential of a matrix? Usually mean the Taylor expansion. And if you go to higher orders, your computations will be very involved. Usually, as I said, I think like it's just the Lie, and then you just keep bringing it over and say, okay, this is going to be.
So we can only do transformation with small alpha.
Yeah.
For
I'm sure,
case,
yeah.
but for abelian case,
And for abelian, non-abelian, this is going to be complicated. But I'm sure like it can be done, and you will maybe mention this. I didn't do myself. I just, I'm lazy. And remember, like, for the abelian case, we had the nu was related to F mu. So that's going to be the same thing here. If you take like the commutator of d mu with d nu, you will get F mu with the sigma. And if you take the definition of the d mu, plug this into the commutator, do the computation, something non-trivial will happen, because if you were commuting d mu with d nu, a mu and a mu were commuting in the abelian case. But now they are not commuting anymore. So that's why you will get an additional term. So F mu that is like, an additional commutator. So this is also new. New, I mean, when you go from abelian to the non-abelian. And then the Lagrangian, the kinetic term is going to be. Now, of course, I have a trace, because the action should be scalar. This is going to okay. So this will be the Lagrangian density of the kinetic part. And you can generalize the rest as well. And
Why does
trace? Because if you take only like a new square, it's a matrix. Matrix. So you need to somehow get a scalar. And of course, trace is not an arbitrary choice. So, and then of course, I mean here. Can you hear me?
No.
I don't need this.
Then it's not recording.
Sorry?
Record.
Yeah. Let's not do this. Then I yell. It's okay, I mean, this I demonstrated like, for the SU2 case, that's why I was like using the Pauli matrices. So if you looking for a higher rank group, this will be replaced by the elements of the H group. Elements of the Lie algebra correspond to the H group. One thing, and then there's the summation of what I is going to go over the dimension of the Lie algebra, and more or less everything follows. But I'm sure you will hear about QCD lecture, or maybe you already have done. I mean, this structure is going to modify the way the gauge coupling is running. I mean, all two must have mentioned about the rest of the gauge coupling, and it's very much related to the matter content in the gauge group. So it can go. Then you can have it as the free theory, or we can have theory which is not, there's different behavior Yeah, this is all I wanted to say. As I said, I mean, I don't think you can start doing hardcore look at a computation with this much. But what I was hoping was
when you pick up a book, or when somebody sells a standard model, you have a better feeling which can see what each invariance means, how to drive, how to put things together, what parameter means. A small portion of what I can tell you in hours. I hope I was able to be successful about this. This is the end of the lecture.